Imagine tiny cosmic bullets traveling at nearly the speed of light, just zipping toward Earth from across the galaxy.
Yeah.
These are cosmic rays, incredibly powerful particles. And, well, figuring out where they actually come from has been this century-old mystery.
It really has.
It's kind of like trying to find a single bottle floating, in the middle of the entire ocean and then trying to trace it back to the factory.
That's a pretty good analogy, actually.
Because galactic magnetic fields just scramble their paths completely.
They absolutely do. That analogy is quite apt because the magnetic fields really do twist and turn the paths of these charged particles. It makes it incredibly difficult to pinpoint their birthplaces.
These pevitrons, right?
Exactly. These pevitrons, the cosmic engines, sort of capable of generating particles with peta-electron volt energies.
Right, peta-electron volts. And just to give you some perspective, we're talking energies like 1,000 times higher than TeV particles.
That's right, which themselves are already 1,000 times more energetic than JeV particles.
Yeah.
So, truly extreme energies.
Mind-blowing stuff. So, okay, for a long time, the leading candidates for these galactic pevitrons, they were the explosive aftermaths of dying stars, supernova remnants, SNRs.
That's been the thinking, yes. When a star explodes, it sends out this massive shockwave.
Right.
That shockwave slams into the surrounding gas, creating intense magnetic fields. And those fields should, in theory, be perfect particle accelerators.
Okay, should be. But there's been doubt.
Well, they are indeed known to accelerate particles, certainly up to JeV and even TeV energies. That's well established.
Okay.
But the doubt has always been about whether they possess the sheer power needed, the oomph, if you like, to launch the most energetic cosmic rays we see coming from within our galaxy, those specific PeV energy ones.
And there's that example, right? Tycho's supernova remnant, the one from 1572.
Yeah, imagine studying the leftovers from that long ago.
It's amazing. But the recent studies from 2023, they suggested something problematic.
Exactly. The analysis suggested that, well, at least in its current state, today, the magnetic fields around Tycho's shock front just weren't strong enough. Not strong enough to create those super high energy PeV particles.
So if Tycho was like typical,
Yeah.
if that's how SNRs usually evolve,
Then how could they be the source of these galactic heavy hitters? That was the big question. It cast significant doubt.
but now there's a new twist.
That's precisely where the new development comes in.
Yeah.
Our sources are highlighting these detailed numerical simulations, published just in 2025 by a small international team.
Okay.
And this research, it offers a potential way out of that whole conundrum.
Right. And that's really our mission in this deep dive, isn't it? To unpack this new research,
Yep.
see how it maybe revives the idea that SNRs are pevitrons after all, explore the observational evidence astronomers are now hunting for, and just understand this ongoing quest. It's a mystery over 100 years old. Okay, let's unpack this.
Let's jump right into those simulations then, because here's where it gets really interesting.
Yep.
The team included complex factors in their models, things that maybe previous simulations had to simplify quite a bit.
Like what kind of factors?
Things like the detailed nonlinear feedback loop between the accelerated particles themselves and the magnetic turbulence right there in the shock front.
Yeah.
They modeled a much more dynamic, kind of messy environment.
So not smoothing things out, trying to capture the chaos of it all.
Exactly right. And their key finding, the really crucial bit, is that supernova shocks can actually reach the necessary conditions. They can accelerate particles to PeV energies, but, and this is the critical caveat, it happens only briefly.
Fleeting phase. So the power isn't constant, it just flares up.
Precisely. The simulation suggests there's this narrow window. Very early in the shock's evolution, we're talking maybe only for a few years, perhaps a few decades right after the explosion.
Wow, that's short on cosmic scales.
It really is. And in that window, the magnetic field amplification spikes dramatically, becomes incredibly strong very quickly. It's this intense but temporary phase that could provide the sheer force needed for PeV acceleration.
Okay.
This brief burst of power, that's the heart of the revived hypothesis.
Okay, that makes sense theoretically, this brief, intense phase. But is there any concern that maybe the simulations, even these new fancy ones, might still be a bit too idealized? I mean, real cosmic environments, they're incredibly complex, right? And varied.
Oh, that's a fair and absolutely crucial point. Simulations are always models, aren't they?
Yeah.
And they always rely on certain assumptions. about the starting conditions, the physical processes involved. But these new models, they're incorporating significantly more of that complexity than previous attempts.
Uh-huh.
They're pushing closer to a realistic picture.
But the real test,
The real test, of course, comes from observation, seeing if we can actually detect this happening.
which brings us neatly to the predicted observational fingerprints. If this theory about the fleeting phase is right, what should astronomers actually be looking for out there?
Well, the new models don't just say it's possible. They predict specific characteristic signatures, things we should see in the multi-wavelength emissions coming from these young SNRs.
Young ones specifically. And multi-wavelength, you mean looking across the whole spectrum, like X-rays, gamma rays, radio waves, seeing how the shock behaves differently in different kinds of light?
Yes, precisely that. If astronomers can find these specific patterns, these signatures, around young supernova remnants, maybe certain shapes in the energy spectrum, or unusual brightness in specific wavelengths, that would provide really strong evidence. It would support the idea that collapsing stars are the primary Pevotron candidates in our galaxy, even if it's only for that short early period.
This naturally brings us back to Tycho then, the one that, well, seemed too weak when they looked in 2023.
It does. Because that analysis of Tycho's magnetic field, it might have simply been looking too late in its life cycle, many centuries after the explosion.
So the party was already over.
Potentially, yes. The simulations suggest that the necessary powerful acceleration phase, that brief Pevotron activity, would have occurred within the first few years after the 1572 event, an epoch that's now long, long past.
Okay, so that raises a really interesting question. Could archival data, maybe, from older X-ray or gamma ray telescopes that just happened to observe Tycho early on, maybe by chance, could that hold hidden clues?
It's possible. A long shot, perhaps, but worth looking into. And, maybe even more importantly,
Yeah.
can we find analogous signatures, those specific multi-wavelength fingerprints the models predict in other younger remnants? Remnants that exploded more recently, say within the last few decades or centuries.
Right. Ones that might still be in that phase or just finished it.
Exactly. That's where the real observational push is now.
So the hunt is definitely on for those specific signs in young SNRs. Based on the sources, what are the absolute core questions driving the researchers right now? What are they really trying to nail down?
Well, the central question, the big one is, can magnetic field amplification really reach these predicted fleeting PV accelerating strengths in reality out there in space?
Okay.
The simulations say it's possible, but brief. So the challenge is finding remnants that are right in that specific narrow evolutionary stage predicted by the models.
Catching them in the act.
Catching them in the act. It's like trying to catch a wave at its absolute peak right before it crashes. Incredibly difficult to time perfectly.
Yeah, that really makes you appreciate the challenge astronomers face. It's not just about building bigger telescopes, is it? It's also about precise timing and maybe a bit of cosmic luck.
Absolutely. Luck plays a role. They also really want to understand how the environmental factors play into this.
Like the neighborhood the supernova explodes in.
Exactly. Things like, how dense is the surrounding gas the shock is plowing into? How turbulent were the pre-existing magnetic fields in that region before the star blew up? Even the potential effects of, say, a binary star companion. If the supernova wasn't from a lone star,
Yeah.
how do all these things influence the acceleration process?
Yeah.
And maybe the duration of that fleeting phase?
Lots of variables. And what about the definitive signals, the things they're looking for that would just scream Pevotron activity happening right now? What are the smoking guns?
The sources mention a couple of key markers. One is detecting a specific feature in the gamma ray spectrum, a sort of hard spectrum feature, sometimes called a pion bump.
A pion bump.
Yeah, it's a telltale sign of ultra-high energy proton acceleration. When these super-energetic protons slam into the surrounding gas, they create particles called neutral pions.
Okay.
These pions decay almost instantly into these very high-energy gamma rays, creating that characteristic bump in the energy spectrum. Seeing that would be huge.
Got it. And the other marker?
The other would be exceptionally bright, non-thermal X-ray rims right at the very edge of the shock front.
X-ray rims.
Yes, these are X-rays produced by the ultra-energetic electrons spiraling in those intense magnetic fields that the simulations predict. It would be a powerful signature of acceleration happening right there, right at the shock boundary, just as the theory suggests.
Okay, so armed with these theoretical predictions from the 2025 simulations and these target signatures like the pion bump and X-ray rims, what are astronomers doing now? Where are they actually pointing their telescopes?
Well, they're already turning telescopes towards known young, energetic supernovae. The source specifically mentions SN 1987A.
Ah, yes, in the Large Magellanic Cloud. Relatively
Right,
close.
exactly. Relatively close and still quite young by cosmic standards, so it's a prime target. They are hunting specifically for those predicted gamma ray flashes, perhaps fleeting ones and other signatures that would betray PAV acceleration happening there now or maybe having just happened recently.
And this is where that multi-wavelength strategy becomes so absolutely vital, right? You can't just look in one type of light and hope to see the whole picture.
Absolutely not. Looking across the electromagnetic spectrum is key. It's essential because different parts of this whole cosmic ray acceleration process, they show up best in different wavelengths.
So like radio waves tell you one thing.
Right. Radio telescopes primarily track synchrotron emission from less energetic electrons spiraling in magnetic fields.
Okay.
Then X-ray telescopes, they map the structure of the superhot shocked gas, but they also capture that non-thermal emission from the higher energy electrons we just talked about, those bright rims.
Gotcha. And gamma rays.
Gamma ray observatories. They capture the highest energy photons, the ones produced by the most powerful particle interactions, like those pion decays that could create the pion bump. They probe the very highest energies directly.
So each piece adds to the puzzle, but you really need all of them together to get the full story.
Exactly right. And coordinating these observations is crucial, especially during the earliest stages of a supernova shock. Ideally, observing within days, weeks, and months right after the explosion is first detected.
Catch it really early.
Yes, that's absolutely crucial if we want any chance of trying to catch Pevotron activity in the act during that predicted fleeting, intense phase before it fades away.
Looking ahead then, what tools are coming online that might help finally crack this century-old mystery? Are there new instruments on the horizon?
Yes, future facilities will be essential. The sources specifically mention upcoming observatories like the Cherenkov Telescope Array, or CTA.
CTA, right. Big project.
Huge project.
Right.
And also next-generation X-ray missions are planned. These instruments are designed to push sensitivity thresholds far beyond what we have now.
So they can see fainter things or maybe finer details?
Both. They'll allow astronomers to delve deeper into the TV and even the PV energy regimes with unprecedented detail and sensitivity.
So the hope is really pinned on these future telescopes, that they could finally catch a supernova remnant in that specific brief moment and provide the definitive evidence, the smoking gun.
That's absolutely the hope, yes. So, to kind of bring it all together, the big picture here is that supernovae, they've long been known as cosmic ray accelerators. That's not new.
Right, but mainly up to lower energies.
Primarily up to lower energies, JIVI and TeVi. Now, thanks to these numerical modeling breakthroughs, it's suggesting this brief, super intense phase.
The 2025 simulations?
Exactly, and the ongoing multi-wavelength observation campaigns targeting these very young remnants. Well, SNRs may indeed be recognized as the galaxy's supreme pevotrons after all.
Wow. All because we're starting to understand this intense but really temporary magnetic amplification phase in the young shocks. That's what provides the necessary boost for those extreme PEVI energies.
Yes. Fundamentally, it helps us unravel one of the biggest questions in high-energy astrophysics. How are particles accelerated to speeds just shy of the speed of light in these incredibly violent cosmic environments?
So why does this matter to you, listening right now? Why should we care about these cosmic bullet factories happening light years away?
Well, because this isn't just some abstract science happening out there in the void. This is about understanding the most powerful particle accelerators operating right here, effectively in our own galactic backyard.
It's fundamental physics on a huge scale.
It is. Fundamental physics, happening relatively close to home, cosmically speaking. It's pushing the very boundaries of our knowledge about how the universe works to how these extreme particles are created. It's a really powerful, dynamic story playing out over cosmic timescales, but with these crucial, fleeting moments.
The ongoing hunt and the promise of these next-generation telescopes maybe catching this fleeting phase in action, it is genuinely exciting. It really is like waiting for that perfect wave.
It really is. And, thinking about that brief, intense phase kind of leads us to this final thought. What does it really mean if some of the most powerful phenomena in the entire universe turn out to be incredibly brief? Maybe only detectable for a very short window in their whole lifespan. How many other fundamental cosmic processes might be hiding like that, just hiding in plain sight, waiting for us to figure out how to observe them at precisely the right time?